Okay, today's video lesson is going to start a brand new topic for almost every single one of you. One of my favorite things to teach and talk about, and that is something known as significant figures, also called significant digits. Sometimes for short, we will call them sig figs or sig digs. So you'll get used to the lingo and what they're called. So basically what I've put on this Post-it is just a sample density problem. So you've got the mass and the volume that have been measured. So we don't know how it's been measured. We just know that we've got a measurement of 2.16 grams and the volume measurement of 118.6 cubic centimeters. So density is equal to mass divided by volume. So when you plug this into the calculator, you're going to get this really long number right here, lots of digits, okay? And so one of the immediate questions that students have when they have a problem like this is, hey, Miss Wood, what do I round to? What do I round to? And there's actually rules for this, and that's the whole reason we have to learn significant figures so that you guys can identify them and round properly. So not that you guys know what any of this means just yet, but by the end of this video, you will. This number right here, the mass, my measured mass, has 3 sig figs in it, all right, or 3 significant figures. My volume has 4 significant figures, okay? Every single digit in the volume is significant. So the 1, the 8, and the 6 are all significant. So we call those sig figs. And the mass, all 3 of those, the 2, the 1, and the 6 are significant. Now, when we divide a number with 3 sig figs by a number with 4 sigs, when we multiply or divide numbers, we have to pay attention to the lower significant digit measurement. So see how this one only has 3 sig figs? Well, when we divide these two numbers and we get this really big number right here, we are limited to only having as many significant figures as our most uncertain measurement. This measurement, the mass, is considered to be the most uncertain because it has the least number of sig figs. So our answer can only have 3 significant figures. So in the answer, that's how I knew to drop all of these digits right here and only keep 3 sig figs. Now your question right now is probably like, well, what about those 2 zeros in the front? And that's what we're about to talk about. You guys have to know how to identify what makes a number significant and what makes it not significant. Luckily for you, there's only 2 instances where digits are not significant, and these 2 zeros are actually called insignificant figures or insignificant numbers. All right, so in this figure, and you're going to get a copy of this tomorrow or today, whenever you're watching this video, this basically breaks down when a digit is significant and when it is not. First of all, one of the things that you need to know, and this is going to be one of the major things I talk about, these are the rules for when a digit is considered to be a significant digit. These are when they're never significant. So the good thing for you is to know that there are 10 digits in our numerical system. All numbers are made up of 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Every number out there is made up of these digits, okay? All 10 of them, 0, 1 through 9, okay? The great thing is that this makes it really easy. The numbers 1 through 9 these digits are always significant, okay? Which you can see that right here. Non-zero digits are always significant. Plain and simple, if it's not a 0, it is always significant. It's this little 0 that gives us headaches. It's the one that is sometimes zeros are significant and sometimes they are not. Now, zeros that are never significant. So that's what we're going to talk about first, are the zeros that are never significant. And the zeros that are never significant are trailing zeros and leading zeros. So trailing zeros with no decimal present, and we'll talk about that a little bit more in a minute. So if you've got the number 40,000, These zeros are not significant. They just hold. Now, are they important to the number? Absolutely. The number 4 and 40,000 are not the same value. These are value. They give value to the number. So they're placeholders, but they are not thought to give precision to a measurement, okay? They are just there to hold the place value, the 1,000, the hundreds, the tens, and the ones place value. The only digit that is significant in this number is the 4. Those 4 zeros are called trailing zeros, and they are just placeholders that hold the place value of the number, but they give value to the number, but they are considered insignificant. Now this next one, here you go. This 0 right here is insignificant. It is just a placeholder. It's just holding the ones place value. That is what we call an insignificant 0. So this only has 2 sig figs right here. All right. That 0 is important to the number, but it's not significant in terms of measurement. All right, the next one only has 1 sig fig. All of these zeros are considered trailing zeros. So trailing zeros are never significant. All right, now leading zeros, which are like this, and students always say, so are these zeros that are like in a decimal number? Yes, these are when you have 0.00, but again, they have to be leading, all right, because we're going to talk about a kind of zero that can be in a decimal-based number that is significant, but leading zeros are never significant. So you have to basically look at it like this. So if I was going to cover up, no, please do that. This right here, does that number have any value? Absolutely not. I've covered up the 2, 3, and 3, and there is absolutely no significance to this measurement because all I see is a bunch of zeros, okay? So there is no significance to the number until you get to that 2, all right? So at that point, then it actually has some significance. So these are also placeholders. They are placeholder zeros. They give value to the number, so they are important. They are just not significant digits. So this number here has 3 sig figs. This one has 2. This one has 2, all right? So these are the only times that zeros are not significant, all right? So anytime you don't count sig figs, it's going to be a 0, and specifically it's zeros that are either trailing zeros with no decimal present. We'll talk about this no decimal present more in just a minute. And then leading zeros, which are at the front of a number until you actually encounter a 1 through 9 digit, the zeros will not be significant, leading zeros. All right, so let's talk about what numbers are significant, what digits are significant. And first of all, as already mentioned, non-zero digits, that is digits 1, 2, 3, 4, 5, 6, 7, 8, 9 are always significant. Now, the 0 is the one that can be significant or not significant. So the zeros that are significant, this is one of my favorites and always the easiest for students to recognize, are what I call sandwich or captive zeros. So these are zeros that are going to appear in between non-zero digits. So right here, this 0 is the 12.01. That 0 is what we call a sandwich 0. So if you have a 0 that has a non-zero digit to the left or right of it, it's called a captive or a sandwich 0, and it is always significant. Even if you had the number like this, 3,000,003. So that's going to be 300,003. All of these zeros are significant. They are all sandwiched between non-zero digits. Now, this is where I have to be very clear. Trailing zeros with a decimal present are significant. So see how this number and this number is different from these up here? So basically, these digits right here, 2,000 with a decimal behind it, that decimal makes all of those trailing zeros significant. If that decimal was not behind 2,000, then the 3 zeros would not be significant. But because there is a decimal there, that means that 2,000 is a certain number, okay? So it is known with certainty that it's exactly 2,000. It's not just rounded, okay? So 2,000 with the decimal behind it makes this significant, all right? Now, same thing for 85.00. Those are considered trailing. If it's trailing, that means it's on the back end of the number, okay? It is behind a non-zero digit, all right? And if there's a decimal present, then it is significant. Now, right here, you can see that you've got a decimal that is after 131.20. So if I had 131.200000, all of these would be significant. Why would they be there if they weren't significant to the measurement, okay? So they are there not, because the thing is, if I got rid of these zeros, you have to think of it like this. If I got rid of those zeros, all right, the number still reads the same value. It's still 131.2, but the zeros behind it mean something. They mean that it was not just 131.2, it was exactly 131.20000. We were able to take it out, the measurement, that far. So, trailing zeros with a decimal present, whether it looks like this or whether it looks like this, okay, these are both what we call trailing zeros because they're at the end of the number behind non-zero digits, and there's a decimal present, so they are significant. However, these type of trailing zeros or this type of trailing zero, these are not significant because they're trailing with no decimal present. So we've gone through those. The last thing to mention is when numbers are in scientific notation. So basically, this is what we call the coefficient in scientific notation, and it's the only thing that we're looking at in terms of significant digits. You do not put it in standard form. Like you would not take this 4.2 or 4.70 and bring it out 24 place values, okay? You just want to look here. This is significant, this is significant, this is a zero that is trailing with the decimal present, so it's significant. So all three of those would be significant, okay? So basically, in scientific notation, zeros will always be significant. If it is correctly written in scientific notation, they will always be significant. So we're going to practice with these. I'm going to give you an image in just a second. I want you to take a minute to see if you can do them, and then I'll go over the answers. All right, so you can see that I've done the first 5 for you. So if you would just pause the video and see if you can look at numbers 6 through 20 and accurately list and identify the number of significant digits in each one. Okay, so I'm going to go over numbers 6 through 20. Hopefully you gave yourself some time to see if you could come up with how many sig figs are in each one of these values. So significant digits, numbers 1 through 9, don't forget. So if you look at number 1, all of these digits would count because they're 1 through 9. There's no zeros. Now right here in number 2, these right here are what we call leading zeros, and although they actually give the number place value, so they're important, we can't just get rid of them because 23 and 0.023 do not hold the same value, okay? So they are important, but they don't give significance to a measurement. So basically meaning that until you get to this 2, there is no value to the number. So 0.023, or I should say significance to the number. So the 2 and the 3 are significant. These are known as leading zeros. They are not significant. In number 3, the first 2 digits, those are significant because they are the digits numbers 1 through 9. They fall in that range. However, 0 on the end, because if there was a decimal behind that, then the 0 would be significant. But it is a trailing 0 with no decimal. Now, there are only 4 digits significant here. Right here in number 5, there are 5 significant digits. All right, so this one does not count on the end because it is trailing without a decimal. But however, all of these digits count because, again, trailing zeros with a decimal present are always significant. So let's go through these. In number 6, all of these digits are significant. In number 7, 3 are significant. The first 3 zeros don't count. The last one does because it's trailing with the decimal present. There are only 2 times that you do not count a 0 when it is trailing with no decimal present, as we see here in this one. All right? Or if it's leading zeros like these, all right? Otherwise, the zeros count. In number 8, there's 2 sig figs, the 3 and the 4. 2, 4, 2, the 3 and the 0 behind it are significant. 1, 2, 3, 4, 5, 6 here. That 0 on the end is not. There is a decimal right here behind the 0 in 780, so all 3 are significant. If that decimal wasn't there, then no, it would not be significant. This is significant with 1. The 1 is significant. The 3 zeros are not. All 6 are significant here. Only 1 here. 3 sig figs here. And number 17. 3 and number 18. 4 and number 19. 2 and number 20. Now I want to quickly go back to the density problems and kind of now apply why these significant digits matter, or look at why they matter, okay? So here's a different density problem. See how we've got 2 measurements? Well, measurements have a certain number of sig figs. This measurement has 3 significant, I just totally messed up, apologize. 2 sig figs, so sorry. Only 2 significant figures, the 3 and the 1. That 0 in the end is just a placeholder. It's holding the 1's place, but it is not significant. Now this has 4 sig figs. Now we'll talk about operation rules more this week, but basically because this is our less certain measurement, so since the mass has only 2 sig figs, we have to follow the more uncertain measurement, which since this only has 2 sig figs, it's the most uncertain one. Whichever one of your measurements that you're multiplying or dividing has less sig figs, it dictates what you round your answer to. So since I only have 2 sig figs here, doesn't matter that we have 4 here. This is limiting me to where my answer can only have 2 significant digits, which means that I only get to keep the 1 place and the tenths place, okay? So basically, this number would be 1 rounded properly according to operation rules and sig figs. The answer to this density properly rounded is 1 point. Oh, I can't get my pen to work. 1 point. Now, since I apologize, my pen is not working. All right, so since the 4 is followed by a 7, and we will review rounding rules, but basically since the 4 is followed by a 7, the 7 will round up the 4, so the density of this, whatever this object is, would be 1.5 grams per cubic centimeter. So we could only have 2 sig figs in our answer since our most uncertain measurement had only 2. You always follow the lesser number of sig figs from your measurements that you calculate with.